All right, so we're going to play. This is kind of fun. We're going to play that same game we were playing yesterday at the end. So all you have to remember here is the kinematic relationships, right? So position is s, velocity is the derivative of position, and acceleration is the derivative of velocity. Okay? And I'd like you to tell me here. I'm going to give you a function, and you're going to have to tell me how to sketch the graphs of the other kinematic functions. So here's what we're starting with. Okay, that is the position function. Okay, that's the position function. So how am I going to come up with the velocity function? Now, choose your words carefully here, but what's the relationship between the graph of the position function and the value at each, like the value of the velocity function for any given input? How am I going to come up with the value of the velocity function at any value of t that you choose based on that graph? How are they related? Okay, what about it? Slope of what? The slope of which kinematic quantity? Position, velocity, or acceleration? I want you guys to say this. What's velocity equal to? Say it again. It is, right? So velocity is the derivative of position, but what's that mean in terms of what I'm looking at up here? What's velocity? How do I know what velocity is going to be based on? Because I don't know what the function is. I just know what its graph looks like, right? I can't do any calculus on this thing. I just have to sketch a graph based on the shape of that graph. What do you think? The derivative of the velocity, you said? The derivative of velocity is acceleration, right? Did you mean derivative of velocity? You got to choose your words really carefully here. What's velocity? We said velocity is equal to the derivative of position, right? Okay, what's that mean though? How does that, so what? What's that mean in terms of this? How is that going to help me? I want to sketch the velocity graph. This is the position graph. Position as a function of time. What do you think? Okay, right. The tangent line is giving me the slope, isn't it? Right? Okay, so if I wanted to know, for example, if I wanted to be able to just estimate what's the value of the velocity function, I want to see what color the velocity function is here. I'm going to cheat for a second and look at the answer. I don't want you to see the answer. So it's purple. That's it. It's purple. There we go. Okay, and acceleration is green. Okay. All right. So if I wanted to know, I'm going to take a picture. Okay, so if I wanted to be able to just estimate the value of the velocity function, right, at t equals 2, what could I do? Becca, what were you saying? At t equals 2. the value of the velocity should equal the slope of position, right? So I'd have to just estimate the slope of that tangent line. So what's that look like? If I were to extrapolate that, that looks like it's, I don't know, like maybe positive 1/2, something like that. Okay. Or negative 1/2. Sorry, negative 1/2. You're right. Negative 1/2. So I'll come down and I'm going to put a value there. That's 1 point on the velocity graph of the velocity function. Right? Everybody see that? Because the slope of this red line is approximately equal to negative 1/2. Right? So therefore, I'm going to get a point down here. The velocity has a value of negative 1/2 because that's what velocity is. Velocity corresponds to the slope of the position function. So I'm kind of having to estimate on these. Is there one place where we know what the velocity is going to be? Where? Where's the velocity 0? At 5, yeah, because look, at 5, we've got a horizontal tangent, right? Horizontal tangent means slope of 0. So if the slope of the position function is 0 at 5, then that means the value of the velocity function is 0 at 5. Where is the velocity going to be maximum? At 10, right? Does that make sense? At 10, because at 10 is where I've got the steepest slope, right? If I look at 10, that's the steepest tangent line. I'm going to say, just going to estimate that's about 1, okay? So that puts me at a velocity of positive 1. Okay, where is the velocity a minimum? Okay, well, it's 0. Okay, the velocity is a minimum for this range of values at 0 because it's the most negative there, right? Does that make sense? Okay, so here I've got a slope of, let's say, negative 1. And so right there. And we're just assuming that it's changing smoothly, right? So we're assuming it's doing something like that. Okay? Where is the speed minimum? It's tricky. At 5. Yeah, the speed is a minimum at 5 because that's where the velocity is equal to 0. If I were to graph speed on this thing, what would the speed graph look like? Yeah, the speed graph would look like it's going to overlap with velocity to here, but speed is always positive, right? So from that point, it would just go, it would be kind of like a V, wouldn't it? Everybody get that? Speed is a scalar. It doesn't have a direction associated with it. So this is a velocity meter per second. If that's the positive direction and it's my motion on a line up here, right? That's a velocity of positive 1. This is a velocity of negative 1 meters per second. This is a speed of positive 1. What's this speed? What is it? Positive 1, right? Speed is just the magnitude of velocity is really all it is. Velocity just attaches a sign to that based on the direction, okay? Okay, so now we've got our velocity graph. What about acceleration? So acceleration, the value of acceleration is equal to the slope of velocity. Okay, well, what's the slope of the velocity graph everywhere? Looks like it's 1/5. That makes sense? Because I'm rising by 1 and running by 5. And it's constant because it's a line. So then my velocity, or sorry, my acceleration function is just going to look like this. Okay, everybody see that? So let's label this stuff. This was position. This was velocity, which is s prime of t, right? The derivative of position. And this is acceleration, which is v prime, which is, if we want to go one step further, it's s double prime, derivative of the derivative, or the second derivative. Okay, give me thumbs on that. How are we doing? We need a little more practice, don't we? Yeah. Okay, let's try. Oh, and let's go, I want to go back. Okay, so if I turn on these other graphs, how'd we do? Well, there's velocity. There's acceleration. Okay, question?
Can you explain, okay, so for the purple line, how did you get one and negative one again?
Yeah. Okay, here, let me, so how did we get one and negative one? Because the value, and like this is, I'm gonna say this twice because this is the thing. This is the one sentence you got to really absorb. If you absorb this, the light bulb goes on. The slope of the position graph corresponds to the value of the velocity graph, right? Because velocity is the derivative of position, and what that means is the slope of the curve, the slope of the position curve, right? So if I pick a value of t, and here's a way to show that. Let's see, I'll do this. Okay, so here, if I just drag this vertical line across, when t equals 10, what's the slope of the red curve there? Because that's the position function. That slope, I'm just estimating that slope is positive 1. I'm going to rise by 1 and run by 1 on that tangent line. Does that make sense?
Yeah, I was like trying to look for the rise over run and it just wasn't making sense.
Yeah, well, and so the rise over run, you'd have to draw the tangent line in to see that, right? And so that's got a value of positive 1. And then if I scoot over here, whoops, no, that's not what I want to move. If I scoot this guy over here, does that make sense there? That's tangent line. If I drew a tangent line in there, its slope would be negative 1 over 1, right? Okay. Does that help? Okay. All right. Try this guy. Okay. Why don't you just try this on your own on a piece of paper? There's scratch paper up there if you want. I've got graph paper up there on the first shelf, white paper on the second shelf, or just use your notebook. But just try that for a second. Work with your neighbor, consult with your neighbor, and see if you can come up with, that is the position function. See if you can come up with the velocity graph of the velocity function and the graph of the acceleration function. Okay, what do we got here? So can you tell me some values that I could plot for velocity? What do you think? Tori, you got some ideas? Jonathan, you got an idea? At 3 it'd be what? At t equals 3 you're talking?
Oh, yeah. Sorry.
Okay, at t equals 3, so that's right here. What? Give me a value. Yeah, like about 0.5. I'd say that's about right. Rises by 1, runs by 2, maybe if I drew a tangent. I'll buy that. So something, something like that, right? So roughly, 0.5-ish. Okay, I'll buy that. Anyplace else? 5 looks like it's about 1, doesn't it? At 5, the tangent, that looks like I'm rising 1 and running 1. Okay, so, oops, that should be positive though, shouldn't it? I gotta fix that. I made that negative for some reason. I am recording. Thank you. I thought I forgot. Okay, there's 2 that you can tell me without even having to estimate, that you can tell me exactly what the slope is though. What are those? 0 at 10. Yeah, look at that. I've got a horizontal tangent. These are the first ones you should look for. There's a 0 value and at 0, right? At 0, I have a horizontal tangent. You always look for those horizontal tangents first. Okay. And then, so what's this thing going to do? Yeah, it looks like it's increasing, starts at 0. The slopes are increasing up to a maximum. The steepest slope is at 5, agreed? And then they're going to decrease but stay positive going back down to 0, right? Now, if we make the assumption that this velocity is changing smoothly, uniformly, we could just do this. Oops, wrong line. Oh. Okay. Everybody buy that? Okay. Slopes increase from 0 up to 1. They decrease from 1 back to 0. Okay. That makes sense? All right. All right. We're not going to do acceleration on this one yet for a reason. We'll come back to this for acceleration. Okay. You want to try one more? Okay. And if we look at this guy and we just turn on velocity, yeah, we were correct. Okay, that is the actual velocity right there. Okay, let's try one more. And then I'm going to move on to something different. We'll come back to these though. I just want to plug in a little bit more stuff before we go further. Okay. There you go. Start with the easy points. There's position. Find velocity for me. So we're finding derivative. In other words, we're trying to sketch a graph of the derivative of this function. What can you tell me about this one? What are some values? Are there any values I know for slope? Which one, Abby, what do I know? Okay, I have a horizontal tangent to the position function, slope of 0 at 5. So there's one point that I could plot. I am recording. Thanks. Thanks, though. Okay, can you find any other points that we could? We don't need a ton of them. But like, what about at 0 and 10? What would the slopes be there, do you think? Looks like 1 at both places, positive 1. And then what's the slope doing? Doesn't that make sense? The slope is starting off very positive. It's getting less positive, 0. small positive, bigger positive, bigger positive, bigger positive, right? So, but we'll assume that they're lines, because if we're just going to make the assumption, and they are, we're just assuming that this is changing smoothly, changing regularly, the velocity is, okay? So then we just end up with this picture. The same velocity graph? It could, but we'll get to that soon. I'm going to ask you that very question soon. Okay. All right. Everybody good with that? Question? It's zero, because if I right here, if I look down here, it looks like it's rising by the same amount that it's running. If I just I'm just estimating. If I drew a tangent line, right? Does that make sense? Like if I made this tangent line bigger, I'm just saying that the slope triangle, I would rise by like 3 marks and run by like 3 marks on that tangent line. Okay. Okay. Give me thumbs on this. Is it getting better? Are we getting there a little bit? Okay. Good. Good. We'll come back to this too. We're not done with that game. We'll come back to it. But I want to skip ahead a little bit for now. And just so you can see, this is the actual velocity function. So we were right. Okay. Okay, so I want to show you one other thing. I want you to see there is an alternate form of the difference quotient that we could use. We don't have to use, we use f of x plus h minus f of x over h, right? That's the one we usually use, but I don't have to. I could just as easily do something like this. I could define this point as having coordinates a, f of a, and this point as having coordinates x, f of x, and then rise over run would just be f of x minus f of a divided by x minus a, right? If I did my rise over run slope triangle. Everybody see that? Right, if I made a slope triangle out of this, from this point to this point, my rise is just the difference in the y values. That's going to be f of x minus f of a. And my run is just the difference in the x values, x minus a. Okay? And so I could then just take the limit of that if I wanted to. I could take the limit, here it is right here, the limit of my difference quotient as x approaches a, for example. Okay? And that's another way that I could shrink those 2 points down into one single point and make the secant line a tangent line. So there's the other form of the difference quotient that we can do. Okay. This is the way we usually do it. This is the alternate version. And then remember, if I want to calculate something like, if I want to be specific, and if I use either this version or this version, notice that I'm being general. I'm coming up with derivative functions. F prime of x is a derivative function where I can plug in any value of x and it'll spit out the value of the derivative for that value of x, right? It's totally general. If I want to be specific, I could do that too. I could calculate specifically f prime of 5 by just replacing the x with a 5 and taking this limit. I could also just calculate f prime of x and then plug in 5. Okay? Either way, doesn't matter. We'll do it both ways, time to time. Okay, so let's try a problem. Let's practice, let's kind of shift back to calculus mode here a little bit. So we want to, ultimately what we want to do is we've got this function down here, f of x. We want to find the line normal to the curve at x equals 2. Okay, what's a normal line? Do you know? You remember from Algebra 2? Probably not. Yeah. So normal lines are lines that are perpendicular to a curve. So they're going to be perpendicular to the tangent line at the point of tangency. Okay. Does that make sense? So how could we approach this one then? Yeah, take the, well, not inverse, I take the opposite reciprocal. Okay, so we need to find the slope, which is a derivative issue, isn't it? So I'm going to have to calculate the derivative function. And let's calculate the derivative function, and then we can just plug in x equals 2. Okay? So where do we always start? This is good practice. Where do we always start when we're taking a derivative? But I mean, like, what do I write down first? Remember, we start completely general, and then we'll get specific for our problem. So yeah, we got to write down what's the definition of a derivative, right? So what's the limit definition of a derivative? So we've got f prime of x equals, you tell me, the limit of what? What's the definition of a derivative again? Limit of f of, okay, of x plus h minus f of x, good, over h as h approaches 0, good. Okay, so that's our starting place every time. Now let's get specific. Okay, so what is our function? Instead of f of x, we can plug in, well, we know f of x is x squared plus x minus 3. Okay, so then what is this part, this expression right there is going to become what? I want to say f of x plus h. What would that look like? Say it again.
X plus 2 squared plus x plus 2 minus 3.
X plus, where'd you get the 2?
Aren't we solving for what's at 2?
Yeah, but h,
H.
yeah, but that's not the value of h. That would be the value of x. I could plug in 2 for the x's, but let's not. Let's just calculate the derivative function first and then plug in 2. Right, so we're not even worried about what value of x we're going to plug in yet. We're just trying to calculate the derivative function first. Okay, but what is that? If f of x is x squared plus x minus 3, what's f of x plus h? What's f of a? What's f of a? A squared plus a minus 3. Hand squared plus hand minus 3, right? So what's f of the quantity x plus h? Okay, the quantity x plus h squared. Keep going. Plus x plus h minus 3, right? That is f of x plus h. Okay, minus, oops, so here's, oh, come on. There's my minus sign, right? And now we want to say this part, f of x. Well, f of x, what's that? X squared plus x minus 3. What do I need to do there, though? Okay, good. So I'd have to put parentheses or brackets around that, wouldn't I? Because I'm subtracting the whole thing. Subtracting f of x. Okay, all over h as h goes to 0. And now we just roll up our sleeves and flip into algebra mode, right? So we'd have to expand this whole thing out. So what is the quantity x plus h squared? Good. X squared plus 2xh plus h squared. Okay. And you can, I mean, if you want to know that for sure. I'm going to force you guys to, I know we need to do this. I just haven't had time to put this in yet, but we'll have a little memorization test over some trig stuff and some of this stuff. So you have to memorize this because you just need to have it available. Plus x plus h minus 3. And I distribute the negative sign, and I get minus x squared minus x plus 3 all over h as h goes to 0. Do I get any good horizontal cancellation here? The x squareds go away. Good. What else? The 3, yeah, the 3's go away, don't they? Anything else? Yeah, the x's. In fact, every term that doesn't have an h, a factor of h in it, is going to go away. Okay. So we get the limit then of xh plus h squared. Oh, 2xh. Yeah, I forgot to put the 2 there, didn't I? Yes. 2xh plus h squared plus h, right? As over h as h goes to 0. Okay, I still can't evaluate this directly or I get 0 over 0, but what can I do now? Factor out an h. Yeah, exactly. Every time it's going to work that way. So I get the limit of h times 2x plus h plus 1 all over h as h goes to 0. I get my vertical cancellation here. So those guys are gone. And now I can evaluate the limit. Let h go to 0. If h goes to 0, then this term goes away, and I just get the answer 2x plus 1. How about that? So f prime of x equals 2x plus 1. That's our derivative function. That's great. So I can plug in any value of x I want. Well, we want 2. We want to know what's happening at x equals 2. So f prime of 2 is just 5. Okay, so that's the slope of the tangent line. We're looking for the normal line. So what's our slope going to be? Negative 1/5, isn't it? So the slope of the normal line, that just means perpendicular. That's our perpendicular symbol. So the perpendicular slope is negative 1/5. Okay, good. We got a slope. We just need a point, but that's easy. If x is 2, I need an ordered pair. Well, what's the y value going to be when x is 2? Yeah, it's going to be 3, isn't it? I'm going to plug 2 in. F of 2 is going to give me 4 plus 2 minus 3, so I get 3. So now I've got a point, I've got a slope, I'm done, essentially. Right? So my line is just going to be y minus 3 equals negative 1/5 times x minus 2. And if they want it in slope-intercept form, just distribute the negative 1/5 and add 3 to both sides. Okay? All right, give me 1 to 5 on that. Is it getting better? Okay, good, good. Question?
So when you try to find a derivative function, you'll do the derivative of f of x. So it's basically the difference quotient.
It's the limit of the difference quotient as h goes to 0. Yep. Yeah, so we usually use this version. We could use this version too. There are certain instances where using this version actually is helpful, but honestly, I don't really need you to be experts at taking derivatives using limits because we're not going to do that very long. Pretty soon we're going to have a better way to do it. Yes?
Okay, so going back to the problem.
Mm-hmm. Yes, right. So f prime of 2. So this right here, what does this mean? So this part, so this is the slope of the tangent at x equals 2. Okay. In other words, the slope of the curve at x equals 2. Okay, so when are we out of here? 55? Okay, so we don't have long. So let's just, this is what we'll talk about tomorrow. And then I think you guys are going to need probably, I could see giving you a little time on Friday to work and get questions answered. So differentiability. So what does that mean? So to take a derivative is the verb associated with that is not derive, it's differentiate, which is kind of weird. So to take a derivative, I'm going to write that down. Or calculate it. We say take a derivative in calculus. Equals to differentiate. That's the verb. And so we talk about differentiation as being the process of taking derivatives. That's what we're learning to do. This is called differential calculus. This calculus that we're doing now, the calculus of derivatives, is differential calculus. So differentiability just means, it's kind of a weird statement, but differentiability means, oh, that's not the one I wanted. Oh, well. Differentiability means take the derivative ability. You know, where are we able to take a derivative? There are certain places where we can't differentiate, where derivatives will not exist. Okay? These are the places. Functions fail to be differentiable. So the derivatives don't exist at discontinuities. Any place there's a discontinuity, the derivative cannot be calculated. It doesn't exist. This is a really important statement in calculus. Differentiability implies continuity. So in other words, to be able to differentiate something, it must be continuous. Okay? Continuity does not guarantee differentiability, though. You see, that statement only goes one way. There are functions that are continuous and not differentiable, but if it's differentiable, it must be continuous. Okay?
So there's still continuity.
Say it again.
Are we still dealing with continuity?
Oh, yeah. Continuity never goes away. So any discontinuities or other places where limits don't exist, we can't differentiate. Sharp corners, we'll talk about why tomorrow. But any place where you have a sharp corner, a sudden change in slope, derivatives don't exist. Any place where there are vertical tangents, they don't exist, which makes sense because a derivative corresponds to a slope, and that's where slope is undefined, right? And then kind of a subclass of vertical tangents would be cusps, which is where you get infinite slopes that form like a really, really sharp corner. We'll look at examples of all 4 of those tomorrow. What's that? Yeah. Let me go down. Here. To there? One more. To there? Okay. Okay, and I'll publish these notes today too. So they'll be on, you can get to them through Planbook.